All right, this is the Geometry Unit 4 Lesson 6 video, or what we call coordinate proofs. A coordinate proof is a proof in geometry where you use the actual measured distances of geometric figures to make statements and conclusions about them. So these are in some ways a little bit more straightforward, but I'm going to walk through each one of these proofs in this lesson. There's really no new information. It's just using things we've already learned to kind of do that, to kind of do coordinate proofs. So I'm going to walk us through these, and then what I'm going to do for the practice test is I will give you a few examples like the ones you will see on the test. So use this lesson as a way to familiarize yourself. But in general, we're going to be using the formula for distance between 2 points. We're going to be using the formula for midpoint, and we're going to be using the area of a triangle formula. So I will post those in the notes page for this, and I'll note here when we use them. But a lot of times you don't actually even need to use those values because especially if it's graphed along a straight up and down, up or down, up and down, or left and right line, you can just count the spaces. And I'll show you what I mean in this first example. So they've given us these triangles, and what we want to prove is based on the locations of the points, we want to prove that these triangles are congruent. So there's a couple of different ways that, or a couple of things we need to prove first. And what they're going to have us do is they're going to first have us prove that EF and GF are congruent. And so we can do that really easily, again, using the distance formula, but really even easier would be just to count. We can see that EF is a measure of 1, 2, 3 units, and FG is a measure of 1, 2, 3 units. So then we can go down here and say, okay, well, this has a measure of 3 units, and the length of GF is 3 units. So then EF is congruent to GF, which is what it says right there. All right, then it says DF is congruent to DF, and that is what we call the reflexive property. Remember, reflexive property is anytime we have two things that are equal to itself. So DF and DF. So if we look, we can see that we've now got a leg and a leg of each triangle. So just to kind of highlight that, we have a leg here and here, and a leg that they overlap. And so that would be the leg congruent statement. And so we would say what we're trying to prove, which is right here. So DEF is equal to DGF, and that's the end of that proof. So you can see what I mean when I say they're pretty simple. You're just looking at the different distances in that diagram. So let's look at this next one. It says we're given the fact that we have AB with endpoints 0, 6 and 8, 0, and midpoint, or endpoint M 4, 3. And we are wanting to just find the length of AM. Okay, so we're going to find the length of AM. So we're going to use the distance formula. They've gone ahead and given it to us right here. So when we go to plug things into that formula, it's going to look like this. Again, we're doing AM. So we're trying to go from here to here. So we'll make A be 0.1 and M be 0.2. So x2 is going to be 4 minus 0 squared plus y2 is going to be 3 minus 6 squared, and the square root of that entire expression. Run over here. 4 minus 0 is 4 squared. 3 minus 6 is negative 3 squared, all still under the square root. Then we have the square root of, and then 4 squared is 16. Negative 3 squared is 9, which equals the square root of 25, which equals 5. And so we would say that that is the distance. Then we get to the next problem. Similar idea. We're going to use the distance formula for M and B. Let's look at this. We're now looking at this line segment there. So x2 is going to be 8 coming from the point B minus 4 for x1 squared plus x2, or y2 is 0 minus 3, again, coming from B and M, all under the square root. 8 minus 4 is 4 squared, 0 minus 3 is negative 3 squared. Again, all into the square root. Then we get, sorry about that, 4 squared is 16. Negative 3 squared is 9. Square root of 25, which you'll notice there is the same as the previous problem. So we've just proven that m is the midpoint of that because the two parts of that line segment are equal. Next one says you have square ABCD with the vertices as shown. And we want to prove that the area of the triangle BCD is half the measure of the area of square ABCD. So we're going to calculate the different areas. We're going to find the length of DC, but I don't really think we need to do the whole formula here because we can see that it's 1, 2, 3, 4, 5, 6 units without even doing the calculation. 6 units, so that's answer choice E. Find the area of ABCD. Now they do a bad job of the formula here. This formula should say A squared or S squared. So the formula is the side length squared. Well, we know that it's going to be S6 squared, which is 36, or answer choice C. So just to be clear, S squared is 6 squared, which is 36. Find the area of triangle BCD. Well, the B and the H are both going to be 6 because you can see here we have 6 here. Because it's a square, we also know that we have 6 here. So that equals H, that equals B. So we're finding the area using those two values. So it's 1/2 6 times 6, or 1/2 of 36, which is the same as 18. So we go down, we see that answer choice D is 18, and that is half. So the area of triangle BCD is equal to half the area of the square. That's answer choice H. So again, we're not using mathematical properties so much as we are verifying that this information is actually true. Samuel promised to call his wife after he was halfway between Dallas and Austin. However, the odometer on his car doesn't work, so he needs to know which city is close to the halfway point. Use the midpoint formula to calculate the coordinates of the halfway point. Well, we can see, you could use common sense for this one. We know that there's this line segment here, and we want to know about the midpoint. I can tell you right now, I'm pretty sure it's going to be Waco for that midpoint. But we can go ahead and do the actual work of it. So let's work it out just to verify. So Dallas is 412, Austin is 0, 0. So that makes it pretty easy because x1 is 0 plus x2 is 4 divided by 2. At y1 is 0 and y2, sorry, I'm trying to erase there. y2 is 12 divided by 2. So we come down here. 0 plus 4 is 4 divided by 2. 12 divided by 2 over there. And then that ends up being 2, 6. And if we go up and look at our graph, we can see that Waco's about 2, 6 in terms of where it's located. And so that makes a lot of sense. Oh, and then that's the answer to number 6. What's the closest town? Well, it's going to be Waco.